Okay, you guys, finally some calculus. Let's define, this is section 13.2, calculus of vector valued functions. Let's define the derivative of a vector valued function. So, okay, let's use symbols here. R prime of t using the prime notation. Okay, what does this stand for? This is the derivative of the vector valued function r. So, what is it? Well, it should involve a limit, I would think, right? A limit as h goes to 0 of, okay, r of t plus h minus r of t all over h. Assuming this limit exists, which it doesn't always, okay? Assuming this limit exists, this is the definition of the derivative of a vector valued function with one variable. Looks a lot like what you saw in Calc 1, doesn't it? Remember the difference quotient in Calc 1? This is a vector difference quotient right here. This is a vector DQ difference quotient right here. And it's basically the same formula for the definition of the derivative that you learned about in Calculus 1, except instead of scalar functions, we have vector valued functions here. Okay, so what then might this represent? Does it represent some kind of slope? Well, that wouldn't make sense because it's a vector function, right? Let me draw a picture. Let's suppose you have some curve given by the tips of the vectors represented by r of t. Remember, when we graph a vector valued function, we don't usually graph the vectors as arrows. We usually graph the tips of the vectors, which creates a nice curve. Okay, so suppose then that this vector here is r of t. And you know what? I'm going to, just so you guys can see what I'm doing, I'm going to want to make this look a little bit steeper, I think. So let's just make it a little steeper. Yeah, that'll look better. Okay. So let's suppose this vector is the vector you would get. So I'm actually drawing the vector, and remember the tip of the vector is a point on the curve. And let's suppose that this vector is r of t naught. R of t subscript 0, like that. And then suppose we add h to t naught. So we get this vector, which we could think of as r of t naught. Suppose that's what you get when you add h. So h is some small scalar. Okay? Then if you connect the arrows, this vector in black then, anybody know what a representation in terms of r, what this vector in black would be? It would actually be, if you think about it, r of t naught plus h minus r of t naught. Think about what you'd have to do to put this vector in black in component form. You'd have to take the tip of the black vector, which is given in component form by r of t plus h, t naught plus h rather, minus the tail, which is given by r of t naught. And that's exactly what this vector is. It's the tip minus the tail, isn't it? So that's the vector in black. So what? Well, that's parallel. Look. That vector then is parallel to this difference quotient, this vector difference quotient, isn't it? What's the only difference? You're multiplying by 1 over h. Division by h is multiplication by 1 over h, right? So what then would the difference quotient look like? Well, if h is real small and you're dividing by a real small number, it could actually be a longer vector, right? So I guess I can do it in pink right here. So if we extend this, maybe this vector right here would be that difference quotient, r of, well, it's a specific value of t, t naught plus h minus r of t naught over h. Okay. Now, can you imagine? You have to use your imagination here. I don't have an animation for this right now. Can you imagine what would happen if we take h closer and closer to 0? Then these vectors in green would get closer and closer together, wouldn't they? Can you imagine that? And eventually, as we take h to 0, would you believe, so let me try to redraw the graph in red here. If we take h to 0, then this difference quotient of vectors would approach a tangent vector, wouldn't it? So if you place the tail of this vector at the tip of r of t naught, then I don't think it's too hard to believe that it might actually be a tangent vector. So this vector would represent r prime at t naught. Okay? So imagine this point here shrinking to here, 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 and here. Then this vector here gets closer to looking like a tangent vector if you put its initial point at the terminal point of r of t naught. So then what do we learn from that? R prime of t naught represents a tangent vector. It placed in put a copy of it in the right place, and it can represent a vector that's tangent to the curve at t naught. So that's what we learned. And so that's a nice analogy with what the limit of the difference quotient, the derivative is for a scalar function, calculus 1. That represented the slope of the tangent line, didn't it? At a particular value of x or whatever the input variable was. Okay. So let me say this. Because limits are taken component-wise, it is easy to show that r prime of t, okay, r prime of t is equal to, okay, if r has components x of t, y of t, z of t, then you just take the derivative of the individual components. X of t, x prime of t rather, y prime of t, and z prime of t. This is how we're going to take derivatives. We're going to take derivatives component-wise, which is about as easy as you could hope for. So you get 3 derivatives in one if it's a vector with 3 component functions. Okay? But the rules you learn in Calculus 1 are going to carry over. If you know how to take derivatives from Calculus 1, then you can take 3 derivatives in one problem in Calculus 3, which is what it breaks down to. So let's do an example. Let's let r of t equal 1 over t. I'm going to use ijk notation. 1 over ti plus 16 tj plus t squared over 2k. And of course the directions are going to be find r prime of t. Find r prime of t. Okay, whoops, went too far. So according to what we wrote above, then we should just be able to take the derivative component by component. So, okay, r prime of t, then, anybody remember what the derivative of 1 over t is? It is negative 1 over t squared, yeah. If it helps, think of 1 over t as t to the negative 1 and use the power rule, right? Bring the negative 1 down and subtract 1. You get the opposite of t to the negative 2, which is 1 over, the opposite of 1 over t squared. Okay, and then that's times I, right? So that's the first component of our derivative. This one, I don't know. That's a hard one. 16. Okay. Good. 16j. Full credit, yeah. And then what's the derivative of t squared over 2? 2t over 2, which is just t. So that's it. That's the derivative. It's about as easy as you could expect, I think, right? It's not so bad. It's actually easier than some of the geometry we've been doing lately, isn't it? Okay, let's do another one. If we can take a derivative, we can go backwards, right? We can take an antiderivative. So let's evaluate the integral of the cosine of ti, again, this is ijk form, plus 1 over tj plus 4 root tk. And we'll put in a dt. So we're taking our first indefinite integral or antiderivative. And of course, if you differentiate term by term, you're going to take antiderivatives term by term as well. So integrate term by term. Oh, and the beauty of the ijk notation, by the way, you could, if you wanted to write it this way, split up the integral, right? And it looks just like how the integral splits up over functions added together back from Calc 1, doesn't it? I'm not going to write it that way. There's no point, but you could do it, right? And it has a nice symmetry with what you learned in Calc 1. What's the integral of cosine of t? So that would be sine of t for your first component, so sine of ti. What's the integral of 1 over t? Yeah, so it'd be plus the natural log. Technically, it'd be the absolute value of t, right? J. And then plus what? You could, if it helps, how can you think of this function? 4 times t to the 1/2. So remember, you're going backwards. So you add 1 to the exponent first and then divide by the new exponent, right? So what does that give you? So it would give you, I'll show the step here. It's been a while since you've done this. So 4 times t, if you add 1 to 1/2, you get 3/2, and then you got to divide by that new exponent or multiply by the reciprocal, right? Which is 2/3. So what are you going to get out in front there? Oh, and then we're going to add a constant vector c, by the way. Sine of t, I, plus natural log, I'm just copying down now, absolute value of tj, and then this becomes what? 8/3 t to the 3/2. It should have a k there. And then plus a constant vector, right? Because integrating each one of these components should lead you to 3 constant components, and we could just put all that in one vector. Okay? Any issues there? I mean, it's about, like I said before, it's about as easy as you could hope for. Okay, let's do a graph real quick just to kind of drive some of these points home. C is a vector, yeah. Because each one of these components is going to have, you could add a constant to. So you could either individually add a constant here, add a constant here, add a constant here, or you could just add, well, they'd be different ones, right? C1, C2, C3. Or you could just add a constant C1, C2, or a vector rather, C1, C2, C3. And that's what I chose to do. Okay. Let's do this. Let's sketch the vector valued function r of t equals 1 minus t. So going back to component form, you got to be able to switch between component form and ijk form. In this case, ij form. We'll do the component form, 1 minus t square root of t. And I want to sketch this vector valued function for part A. Oh, okay, we know how to do that. Make a little table with t, x, and y, right? So what would be some good values to plot for t? 0. I think 1 would be good. Maybe perfect squares since we have to end up taking the square root, right? What do we get when we plug in 0 for the first component? 1 for the second component? 0. What about when we plug in 1? Oh, yep. Whoops. I meant to put the 1 there and the 0 there. Okay. And then, yeah, when we plug in 1, we get 0 here, and square root of 1 is 1. When we plug in 4, -3, and 2. All right. I think that'll be enough to get kind of a general idea of what this graph looks like. Okay, so here's x, here's y. Let's see, I need 1, 0, 0, 1, and 1, 2, 3, up 2. So, okay, 1, 0 is here, 0, 1. So these are the ordered pairs I end up plotting, right? And then -3 up 2. Looks like it'll be a curve that has that sort of trajectory. Okay? So there's a point here. I know you already know how to do that, but let's look at part B. Part B, find r prime of t. So, okay, rt is up there. What's r prime of t? R prime of t is what? -1, right? Derivative of 1 minus t is -1, comma, 1, 2, root t maybe? Does everybody believe that? So this is t to the 1/2. Bring down the 1/2. And then subtract 1 from the exponent gets you a -1/2 in the exponent. So square root of t as a factor in the denominator. Okay there? Okay, I'm building a little point here. I want to sketch r of 1 and r prime of 1. So these are actually vectors, so I'm going to sketch those as arrows. What would r of 1 be? We actually already know that. R of 1 is just, when you put it on the curve, it's a 0.01. But when you graph the vector, it goes straight up like that. Can that, oh, maybe I should do pink so it'll show up better. You guys see that? So that pink vector is r of 1. R of 1 in pink. Make sense? All right. And then what would, so that's r of 1. That's the vector 0, 1, right? And then r prime of 1, we haven't computed yet. What would r prime of 1 equal using r prime from part B? Be the vector -1, 1/2. -1, 1/2. Now, I'm going to do something special with this graph to illustrate something. With this vector, I'm going to plot it so that its initial point is at the terminal point or the tip of R1, R of 1. So let's put the tail, on tip of R of 1. So the tip of R of 1 is at this 0.01. From there, I'm going to go, maybe blue would have shown up better. From there, the tip, I'm going to go what? I'm going to go left 1 and up 1/2. If I go left 1, can you guys see that dot? If I go left 1, that puts me there, and then up 1/2, it puts me right about there, doesn't it? Can you see then that this vector in blue, which is r prime of 1, truly does look tangent to the curve in red, right? So r prime of 1 in pink, or in blue rather. And note that the blue vector is tangent to the curve, as long as I place it at the tip of the vector in pink, which is r of 1. Okay? So that's what I showed you in pictures earlier, but this is with respect to a specific problem. Is that okay? Not too crazy yet, right? All right. Let me show you another example. Do you think we can do definite integrals? How about 3t squared I plus tj? Integral from 0 to 2, 3t squared I plus tj dt. Using the same notation as we used in Calc 1, but now we're integrating a vector. Okay. Yeah, well, we're going to integrate term by term, right? So there's no reason why we can't do a definite integral here as well. So let's go ahead and figure out the antiderivatives for each term. What's the integral of 3t squared? So t cubed I, right? T cubed I plus integrate t, you get 1/2 t squared j. And we want to evaluate this from 0 to 2. But that breaks down to evaluating the individual components from 0 to 2. Like so. You see what I did there? Okay, so what do we get? Fundamental theorem, one of the versions of the fundamental theorem of calculus, plug in the upper limit first, you get what? 8, and then minus, plug in the lower limit, that's just 0, right? So 8, I'll put that in to remind you, because when it's not 0, it matters, doesn't it? So 8 minus 0i, or just 8i, plus 1/2 times, okay, plug in 2 first and get 2 squared, which is 4. Plug in 0. 0 squared is 0. 1/2, 0, 4 minus 0, j. So what does that become? 8i plus 2j. You don't have to worry about a constant when you're evaluating a definite integral, right? So I'm given r prime of t. It's 3t squared j. So you don't see I. Plus 6 radical t k, and we want to recover r of t. Now, normally you could just recover it up to a constant like you saw in an earlier problem, but we can do one better here. We can recover the exact function because we're given a little bit of information about the original function. We're given that r of 0, not r prime of 0, but r of 0 is equal to the vector I plus 2j. That's called an initial condition. So given r prime, given the initial condition, you're asked to find r of t, and we can do it. In other words, we can figure out what that vector constant c will be. Okay, so let's proceed like we did in a previous example. Let's integrate. We'll use the usual symbolism. Integrate 3t squared j plus 6 radical t k dt. Notice how I set that up just like a calculus 1 integral with the differential dt and everything, except remember we're going to integrate not term by term but component by component. It looks the same though in ijk form. So let's integrate the j term. What do we get? 3t squared integrate just t cubed, nothing hard there, don't forget the j, plus 6 radical 2k. 6 times t to the 1/2, integrate that, what is that going to turn out to be? T to the 3/2 times 2/3, right? So what's that going to be? 4t to the 3/2, and that's k, right? And then at least for now we need a constant, don't we? So plus a constant vector c. Now this is r of t, so let's label it correctly. R of t equals this integral, and this integral turned out to be this. So if we weren't given the initial condition, we'd stop here. But we do know this initial condition. We know that when t equals 0, you get I plus 2j. So let's use that here on this version of r of t. Let's use that. So r of 0, okay, if you plug in t equals 0, what happens to the j and k components? They turn out to be 0, don't they? And you're just left with c as a vector, right? But wait a minute. We know what c then equals. At t equals 0, it must be I plus 2j. So you can set c equal to I plus 2j. And that tells us exactly what the constant vector equals because it's an initial condition. And not just that, it's because t equals 0 there. So I've got another step to do. I can go ahead and put this c in here and then add corresponding components. So r of t, just to write it out, again, the first part's not going to change yet. T cubed j plus 4t to the 3/2 k plus c is I plus 2j. So this is what we're adding in. We're replacing c with I plus, that's supposed to be a plus sign right there. We're replacing c with what it's equal, I plus 2j. So what can we combine here? Is there another I component other than 0i? There isn't, so let's just put it in the usual order, ijk. So let's put I first then. So r of t then is I plus, we do have a j component here and a j component here. So you have a t cubed for your j here. What do you have for your j component over here? 2, right? So if you want to write it as one component, what do? Remember how we add vectors? We add component-wise. So just put parentheses around the sum since they're not like terms. You could go t cubed plus 2. And then put a j on the end. And then we still do have a k component. What was the k component? It's going to be the same as it was, right? So plus 4t to the 3/2 k. So we recovered r of t, not up to a constant, but because of that initial condition, we recovered the exact function, r of t. R of t is smooth on some interval. T is on some interval for t from a to b. If and only if, IFF for if and only if, r prime of t is continuous on that interval and r prime of t doesn't equal the 0 vector anywhere on that interval. Does not equal, is what I'm trying to say here. Does not equal the 0 vector anywhere on AB. Later on, when we talk about r of t as a position vector, I'll describe why this is a good definition. But for right now, it's just going to ensure that you get it when you draw the curve either in space or in the plane. No sharp points. You get this nice smooth type of curve instead of maybe some cusp like that. No cusp. That's what this definition ensures. You don't get that kind of sharp corner. Okay? Take my word for it. We'll talk more about it later, but that's what it ensures. If you wanted, for example, to find the open intervals on which r of t, which equals 1 over t minus 1, I plus 3tj if you want to find the open intervals on which this vector valued function is smooth, all we have to do is take the derivative and act appropriately according to the definition. So, okay, let's find r prime of t. Help me out here. What's r prime of t? For the first component, it's just like taking the derivative of 1 over t. So it'll be negative 1 over t minus 1, the whole thing squared, right? I. And then plus, what's the derivative of 3t? 3, so 3j. Okay, so, okay, the conditions for it to be smooth. R prime of t has to be continuous. Well, in order for R prime of t to be continuous, the component functions have to be continuous. If you have a constant function, it's continuous everywhere. So don't worry about the j component. When is the I component, this guy, not going to be continuous? Well, it's when it's not going to be defined. So at t equals 1, you have a problem, okay? And that's going to be the only place here. So t cannot equal 1. Well, how do you find it? How do you write that in terms of an open interval? Oh, I should mention another condition on it being smooth is R prime of t doesn't equal the 0 vector. That's the vector where all the components are 0. That's not a problem here, because 1 over t minus 1 is never 0 on its domain. Okay? So you don't have a problem with the derivative being 0. So this is the only problem child. And to write then the open intervals on which R of t is smooth, you just have to delete kind of the 1. And the way we do that is we say the open interval from negative infinity to 1, parenthesis to exclude 1, union with 1 to infinity. So these are the open intervals on which R of t is smooth. Rules for differentiation. So number 1, this is kind of just a review from Calc 1 because it works the same with vector functions as it does scalar functions. If you want to take the derivative d dt of, say, u of t plus v of t, these are vector valued functions. Do you think it splits up nicely? You betcha. On the left side, I'm going to use the Leibniz d dt notation. On the right side, I'm going to use prime notation. Yeah, splits up. The derivative of the sum is the sum of the derivatives, u prime of t plus v prime of t. And that's just because when you take, and you can really see this in IJK form, when you take derivatives, you do them component-wise. So those rules for taking the derivatives of sums of functions will split up among the sum of the components of the sum of the two functions. By the way, do you think it works just as well for subtraction? Yeah, but I'm not going to state it separately. Works for both. What about for a constant? D dt of some constant, c times u of t, let's say. What do you think we can do with that constant? Take it out. So that's the same as c times u prime of t, where u of t is a vector valued function. Okay, d dt of a product like a scalar function, f of t times u of t. Turns out you're going to have to use the product rule. So you take the derivative of the first times the second. Remember the product rule? So the derivative of the first is a scalar derivative plus the first, f of t, times the derivative of the second. The second derivative over here is the derivative of a vector valued function. But it actually looks exactly the same in form as the formula you learned for taking derivatives of products back in Calculus 1. Well, guess what? If you have u of t, vector valued function, dotted with v of t, guess what? You get another product rule. So you get the derivative of the first, u of t, u prime of t, I should say, times the second, dot product times the second, plus u of t dot product with the derivative of the second. So Derivative of the first times the second plus the first times the derivative of the second. It's the same product rule you learned before. And guess what? It works for the cross, whether it's cross product or dot product, it works. You get this is a total of 3 product rules. Isn't that wonderful? Triple your pleasure. No? Oh, sorry. Trying to be optimistic, you guys. Come on. And then, of course, there's the chain rule. DDT. Let's say you take u of a scalar function. You insert a scalar function into the vector valued function. Then it shouldn't come as a big surprise that you can take the derivative of the vector valued function, I'll call it u prime of f of t, and multiply by the derivative of the function inside, f prime of t. And that is the chain rule. Okay? These are your rules for taking derivatives. All right. So to close it out, let me go ahead and define the unit tangent vector. The unit tangent vector, okay, we know r prime of t is a tangent vector to r of t, right? We examined that pretty closely today. All you got to do is divide by its magnitude and you turn it into a unit vector. Remember that? And we give this the name t of t, the unit tangent vector. Okay? And this will become a very important vector later on. It's really easy. It's easy enough to find. So we'll close it out with this example. Find t of t if r of t is equal to 4 root t I plus t squared j plus tk at t equals 1. And this is important. At t equals 1. At t equals 1, okay? So what is r prime of t? You got to take the derivative of this guy, which is 4 times t to the 1/2. So what's that going to be? We're taking derivatives, so 1/2 times 4 is 2, right? Times t to the negative 1/2, which would be what, over square root of t I. And then plus 2tj, would you believe that? Plus k. Would you buy that for $1? 50 cents? At this point, you'll believe anything, right? All right. Now, it's very important. It makes it easier since we're evaluating this at a particular value of t. Find it. Now that you've taken the derivative, plug in 1. This will make life a lot easier. So what do you get when you plug in 1? 2i plus 2j plus k, right? Now, believe it or not, we're almost done. To find t, we just need the magnitude of r prime, and then we'll create that fraction. But since we're finding t evaluated at t of t, evaluated at the scalar t equals 1, we can just right away find the magnitude of r prime of 1, create the ratio in terms of r prime of 1, and it makes life easy. This will be the square root of 9, won't it? 2 squared plus 2 squared plus 1 squared, which is 3. So t of 1, the unit tangent vector at t equals 1 is going to be given by, if you divide or multiply by 1/3 r prime of 1, you'll have it. So it's r prime of 1 divided by the magnitude of r prime 1, which is 3. So that's going to be 2/3 I plus 2/3 j plus 1/3 k. And that's it. And this is just a tangent vector that has length 1.